So we've looked at the file system API and we've developed some intuition about how we want the file system API to behave. What we'll do today is use that intuition to kind of derive and show you how some of the implementation supports those semantics. So you might recall that we talked about different ways that different processes might interact around files, and we concluded some things about data we need to maintain. So for example, if you and I are both running processes and we're both able to read a file, should we be able to see that file's data? The answer is yes, right? If I've set things accordingly and I want you to see my file, we should be able to share that. But let's imagine that you and I are both reading or writing the file. If you're reading at offset 0, should that require that I'm also reading at offset 0 or that the byte immediately after offset 0? And the answer is no, that wouldn't make any sense at all. If you and I both want to read the entire file, then you should be able to start at 0 and read the file, and I should start at any other time and read from 0 and read the file. And the offsets at which these two processes are reading should have no effect on each other. What if my process opens the same file twice? So I actually call open twice. Should I have one file descriptor or two? And the answer here is two, because if I open a file, I'm saying this is a brand new interaction with the file, so give me a new file descriptor. It's almost exactly the same as if two processes had opened the file. Okay, so do these, and given that hint, should these two different file descriptors share an offset? Well, the answer is no, because they're two completely different opens. Okay, but what if I have two threads? So here the model is, I have a process, it opens a file, and now I spawn off two threads. Should those threads be sharing an offset? And I'm going to claim that the answer is yes, because we've only opened the file once, and threads in some sense we know share a lot of data, and in particular, they're going to share the information that the process maintains on its files. So in this case, they would in fact be sharing the same offset. So if one thread reads from block 0, reads from from byte 0 to 4095, and then the next one does a read, it should get the next block. Okay, now let's talk about what happens if a process creates another process. So the way that we create processes in Unix or Linux systems is that a parent process calls a system call called fork. It creates a child process. And in particular, that child process is an exact copy of the parent after fork. And so the question is, are the file descriptors shared? And the answer is actually yes. So because a child is a complete copy of a parent, that actually means that the file descriptors are shared. We only called open once, and now we have two processes that could have the same information. And we'll see how we use that to implement really powerful mechanisms. And so because they share file descriptors, they also are going to share the same offset. So given these facts, we're going to figure out what kind of data structures we need to support them. Okay, so when a process issues the open system call, the return value is this small integer. Now we also know at this point that when a process starts up, it gets three file descriptors that are already open. 0, 1, and 2 correspond to standard in, standard out, and standard error. Now, those are not the same things as the small standard out, standard in, and standard error that you use for things like fprintf. Okay, those things are using standard IO, which is a library, happens to provide caching. So they're accessing the same underlying file, but when you use system calls, you're kind of talking directly to the file system, whereas standard IO is also talking directly to the file system, but when you talk to standard IO, you're sort of going through that. So key observation, you don't want to mix and match. You either want to be going through standard IO and using all the F calls, fopen, fread, fwrite, fprintf, or you want to be going directly to the file system API and using open, close, read, write. All right, so given these facts, the question is, what data structures do we need to maintain? So the first one we need to maintain is every process needs to have its own file descriptor table. right? This is going to be sort of an array that maps from these integer file descriptors we're handing processes to something else. And we'll get to that something else. So here's what the file descriptor is. It's a per process data structure. And when we talk about file descriptor allocation, what we're really talking about is looking at that table, finding a slot, and giving the process the first available file descriptor that we can now use to represent a file. So we know that 0, 1, and 2 are open when the process begins. So the first time you call open, you are likely to get an FD of 3. In fact, you are required on most systems to get an FD of 3. And so what that says is that the fourth entry in the array is where I'm going to store the information about this file. And mostly what this table is going to contain is some pointers to other objects. So now I want to ask the question, can we store the current file offset in this table? And in almost all the use cases that we talked about, you might think, well, yeah, it seems to make perfect sense. Unfortunately, that last case where I talked about parent and child processes suggests that that doesn't work. So here's the way we think about it. When we have a parent and a child process, right? So what happens is the parent exists, the parent invokes the fork system call, and what that does, it says copy the parent, and now we have two identical processes. And as part of that copy, we're going to copy the file descriptor tables. However, those file descriptors are really the same open, and they are going to share an offset. So given that we've copied this, if I also copied the offset, as soon as one process did something, that wouldn't be visible in the other process. So what this suggests is that the offset is actually somewhere else in a data structure that is shared between multiple processes. So what is this thing? So the way to think about it is that the offset corresponds to a unique open. And so we need a data structure that spans processes that corresponds to a unique open. And unsurprisingly, we're going to call this the open file table or just the file table sometimes. And this is a data structure that's going to be shared across all processes. So it's managed by the operating system, as are these file descriptor tables, but it's shared across all processes. And this is where we'll keep the offset. We will also keep a reference count because if we have two processes that are going to share an entry in this table, we can't reclaim that entry until we know that both of these have gone away. And so every time we have like a pointer into this open file table, we're going to keep a reference count. And then it's this open file table that will get us to our single in-memory representation of an object. So we'll have lots of pictures to show this, okay? But before I go to the pictures, I just want to do one more thing, which is, what's this in-memory object? So for historical reasons, we call this in-memory object a vnode, and you can think of it as it's the in-memory representation of this object. And it's going to point to all sorts of stuff, and in particular, it will contain a copy of the metadata that lives on the disk, but when we open the file, we're going to copy that metadata into memory so that I can access it quickly. And part of that metadata is going to be a way to help me find the blocks on the disk that correspond to this file. All right, a lot of stuff there. Let's just start with the management of file descriptors and sort of how that relates to this open file table. So what we're going to do is we're going to step through different scenarios. Okay, scenario one is just a single process. So I have a single file descriptor table. Different entries in that file descriptor table will point to different entries in my global open file table. So in this case, standard in, which is FD0, corresponds to this open file structure, and that is going to correspond to some in-memory object. Okay, so in this case, it appears that I have closed standard in, standard out, and standard error because 0 is pointing to some file called bar, and 1 is pointing to some file that I haven't told you about. So file descriptor table, mostly a collection of pointers to other objects. These objects are shared among the different processes, and they contain in particular the position in the file where you are reading or writing and a reference count. This is then going to point to another set of in-memory structures that contain all the files that the system has open at the moment, and in particular these vnode structures. And those correspond to particular files and have all the metadata associated with it. So now let's assume we have two processes that are just reading the same file. So each of them have their own file descriptor table. They're entirely separate processes. So each of them called open, which means each of them got their own open file structure, right? Two different opens, each of those has ref count 1, each of those maintains their own position, but they refer to the same actual file, so they point to the same vnode, right? They're still gonna get the same data when they read it, but they each have their own open. Okay, that's two different processes. What if the same process calls open twice on the same file? So this actually is going to look very similar, but now we only have one file descriptor table. But if we call open twice, we're going to get two different entries allocated to that open. So in particular, what the system does not do is say, oh, you already have this file open. I'll just, somehow increment a ref rate. No, if you call open, you are telling the system, I want a new FD. So you get this new FD. Again, each open corresponds to its own open file structure. And again, we're talking to the same file. So that's if I'm in open, I'm in a process and I called open twice. But let's imagine that I now have a multi-threaded process. So I'm only going to call open once, but these two threads are both going to do reads and writes. So I've called open only once, which means I have only one file descriptor, and I've only called open once, so I have only one open file table, and that points to a file. And so the two threads are using this exact same file descriptor, and it is really the exact same file descriptor because there's only one table in the whole process, and both threads are accessing it. Okay, and so we want to contrast this from the case where I create a new process. So in this next picture, let's assume I have a parent process and it creates a child. So I copy the parent's file descriptor table to the child. It's a straight copy, just like an array copy. What that means is that these two file descriptors are both referencing the same open file table structure. And that's when we get a ref count of 2. And then that open file table is still referencing the same object. Okay, now there's one other system call that I'm going to introduce, because when we start talking about fancy interaction between parents and children and their file descriptors, it will become useful. And it's also, how else can we get a ref count of 2, right? So one way we get a ref count of 2 is when we have a parent, it forks off a child, all the file descriptors that were open in the parent now get ref count of 2 because we've copied it. And so part of that fork process is in fact updating those reference counts. Here's another way you can get a ref count of 2. There is a system call called dupe and a cousin to it called dupe2. And what that says is, I have a file descriptor open and I would like you to duplicate it. I want you to copy it, right? That same thing that you did when you created a child, I kind of want you to do that, but I want you to do it in my own process. So in fact, if we had file descriptor 2 open and I called dupe, I will get a whole new file descriptor allocated, but they will be pointing to the same open file table. Okay? In case you wonder, like, why would I ever want to do that? The fundamental reason we end up doing that is to support pipes, right? So you know how on the command line you can say, do an ls and put a vertical bar and then take the output of ls and send it to cat or something like that? That is actually supported by clever use of this dupe call. So We'll get to that later. Maybe you saw it in 213, but this is what's happening behind the covers when you do a dupe. You're just saying, copy the information from file descriptor 2 into a new file descriptor. And so the call with only one parameter, you say, this is the one I want to dupe, and it allocates the next file descriptor and gives it to you. This one says, in particular, I would like you to take file descriptor 1, and I want you to duplicate it into file descriptor 2. Okay, but under the covers, both of these will end up with 2 entries in the descriptor table pointing to the same open file table. All right, so on that note, what we've done is we've used our intuition about how the file system API works to sort of uncover the data structures that we must implement in the file system to support those semantics.